Chris Mert from University of Michigan. He is a graduate student of Professor Saraposi, if I remember correct. Yes, he's in the third year of his PhD, and his talk will be on detection of fast neutrons during photon active interrogation.
Hi, can everyone hear me all right and see my slides?
Yes, I can.
All right. Well, thanks for the introduction. Yeah, I'm a third year PhD student. I'll be starting my fourth year this fall. So I'll be talking again about detection of fast neutrons during photon active interrogation. So we can start out with an intro and motivation for this project. If you think about something like passive detection systems, you can imagine that shielded special nuclear material can be a challenge for passive neutron detection. For example, if you consider highly enriched uranium, which is a material that emits relatively few neutrons because it has relatively low spontaneous fission rate. And also, if you think about the photons it emits, those photons are easily shielded because they're lower energy. So to sort of remedy this challenge to passive systems, we can consider active interrogation systems. In specific to this presentation, photon active interrogation systems, where we use an intense photon source, both high energy and intense flux-wise, which can therefore penetrate shielding material that may be used to shield the special nuclear material. And so that'll increase our source term by inducing interactions or reactions inside the S&M. Of course, that still creates a challenging detection environment. And as you'll see, sort of running theme of this and also from Abbas's presentation is that we have an overwhelming flash of photons that will cause pulse pileup. Especially that's exaggerated when we're using pulsed sources like the linear accelerator I'm discussing. One example would be on the upper right. I've shown two sample traces. The black trace is from our linear accelerator. While that curve is non-zero, basically means the LINAC is on and it's emitting photons. The blue trace are example voltage pulses from a still beam detector. You can see some of these pulses are far apart, but some are quite close. That's going to interfere with our PSD because we're relying on those tail integrals and total integrals. And where that shows up when we look at the actual 2D histograms for our pulse shape discrimination, examples on the lower right, we'd like to see a well-defined gamma ray band and a well-defined neutron band. But when there's pileup, we'll see additional features that are not really meaningful for our analysis. In this case, this triangular region, which adds counts in where we might consider the neutrons as appearing. So that's going to be a challenge to our analysis. So the goal of this work is to develop this neural network-based pulse shape discrimination algorithm with the goal to detect neutrons during this pulsed high photon radiation field. And we want to focus on using economical photon sources and economical radiation detectors. And that ties more into the mission relevance. You can imagine if we were to deploy these systems, they would therefore support our mission to detect concealed special nuclear material. And because these systems would have to be deployed on a wide scale, we make sure that they're economical. Being able to deploy more systems would help us further improve the capability to detect the special nuclear material that is shielded and therefore prevent malicious actors from acquiring that nuclear material. And just sort of context, picture from the Port of Los Angeles takes in a great deal of cargo on a daily basis. Ideally, if you wanted to scan every one of these cargo containers, that may not be feasible. But it's important that we have, we'd have to install more than one system, say. We'd have to install enough systems to properly analyze the cargo that comes into that port. So having an economical system helps us to deploy wide. So after discussing this intro, we get more into the approach of this work. We're going to induce these photonuclear reactions in, say, depleted uranium using a linear accelerator. This is an electron linear accelerator that was supplied to us by the Countering Weapons and Mass Destruction Office at the DHS. It is based off of medical, like radiation oncology LINAC. And because of that, it can be considered a relatively mature product. So that lends itself to that low cost that helps us out with that economic aspect. Because it is an electron accelerator, you can imagine this will accelerate electron using electromagnetic field. That photon is going to hit a converter undergo radiative losses and emit photons. Those photons will follow the Bremsstrahlung spectrum. And it's a broad energy range that ends at that endpoint energy of the electron. So this machine can produce photons up to 9 MeV in energy. And that is sufficient energy to induce these photonuclear reactions in materials like uranium, which is the most interesting to us, but also lead and tungsten, which could be considered as surrogates on some level, but also are very common photon shields. So in the upper right, I've just shown a picture of the LINAC in our lab. It's sort of in here in this biological shielding. It's inside a concrete vault, and the beam direction shoots sort of this direction. And I'll show overhead views later so you can put that in context. I also included a few parameters. Most importantly, our endpoint energy, 9 MeV, and also our pulse length is fixed at 4 microseconds. So it's not a continuous wave source. After we induce those photonuclear reactions, we're going to need to detect that emitted radiation, and we're going to use organic scintillators. I believe there have been plenty of presentations that have discussed these organic scintillators, but to sort of summarize quickly, they're sensitive to both photons and neutrons. Neutron sensitivity due to its relatively high hydrogen content. Photon interactions will still occur with this material, but those dominant interactions are going to be Compton scattering, so it will not observe photopeaks. And even as Abbas had discussed shortly, they exhibit pulse shape discrimination. And for example, if we look at these voltage pulses and compare the integral of discrete regions, so for example, a tail integral and a total integral, and histogram them, we will see distinct regions based on the radiation that caused that interaction. So we often observe a photon band and a neutron band. And this is a much cleaner measurement compared to on the first slide when I showed that, that triangular region. For this work in particular, we are using still beam, relatively low cost, relatively high efficiency, and of course it has good PSD ability. I got this picture from a data sheet just to show everyone, get an idea of what it looks like. And the process to create these plots can be considered charge integration. You may hear me say that a few more times in this presentation, but we'll compare that charge integration result to our neural network analysis. So again, a lot of details from Abbas's presentation, so I'll try not to dwell on this slide. But the important part here is that it can decompose these double pulses that have separation like greater than or equal to 60 nanoseconds, which we hope to give us an advantage over charge integration, which would require much greater separation. And of course, close split and cut, which were previously discussed. The advantage being that we can still recover those pulses if they occur, say, in the close region, in the split region, and even in the cut region where we can recover only one of those pulses. That's going to help us get more neutrons, a higher neutron rate with the same measurement time as charge integration or quicker time, depending on how you want to leverage it. But there are some differences between what the current implementation is and what we'd like to do in the future. So, for example, we do not currently analyze quadruple pulses, but there's no reason without adequate training that we couldn't recover that information. So we work in the future to do triple and quadruple pulses instead of just doubles. In principle, we could also recover clipped pulses. So when a pulse falls outside of your dynamic range. Again, it'd be a factor of training. And of course, we'd like to reduce the minimum separation time, which would make us more robust against pileup. So with this technical approach, oh, sorry, this isn't transitioning. We will use that for this experiment I've outlined. We interrogated a sample of depleted uranium, or DU, using our LINAC in the lab. So if you remember the picture of the LINAC on the previous slides, that's sort of from this angle. So we look at the LINAC, you can see the vault wall. A photon beam will travel and irradiate our DU target. This distance is about 10 meters. And we've set up a 2-inch still beam detector at varying distances, but the results I'm talking about today, the detectors are about 3.6 meters from the beam center line or the target location. And that detector is in a lead cave, which I've shown in the lower right. Quite a robust cave to cut down on that photon flux. We're really interested in those neutron counts, so we were hoping that the lead shielding would reduce the photons greatly and still allow us to see some of those neutrons without some pileup. An important point here is the the fact that we have a lot of lead in the room, both for the collimation and also at a beam stop, which would prevent unreasonably high dose to lab spaces that are on the other side of that wall. So that contributes to our active background because the threshold for lead for photonuclear reactions is below 90 MeV. So we do background subtraction for these measurements. So getting the results. First here I've shown on the left what I'd call raw still beam results. So the only pulses that were cleaned were clipped pulses and noise pulses. So what we see here, for example, is a well-defined photon region that would occur in this cloud. And we see this large, sort of sparsely populated compared to the photon region, but still plenty of data points. And these would correspond to both neutrons and pileups that can still be recovered in principle. Photons and neutrons, neutron pulses, as rare as they might be. And on the right, we show the same data analyzed with charge integration. So again, we see how many of these pulses are just rejected by charge integration because it cannot analyze pileup. And so you see this sort of illustrates that advantage. If we can recover these pulses, we're using that data where we would otherwise forsake it completely. So if we analyze the same data with the neural network, these results arise. Maybe the easier to discuss would be the photons. So now you've seen the neural network has classified all these pulses as photons. Quite encouraging because we see that same band structure. There's a few misclassified pulses that we'd still have to analyze for further detail. But also for the neutrons, we see more pulses, and it has some semblance of a band structure, which is quite encouraging. Different structure than the charge integration results. And this, of course, this merits more investigation, but it's still nice to see a gain in neutron pulses and also some relation to an actual structure. So those are sort of preliminary results. Before I get to conclusions, I'd like to discuss those impacts. Of course, the successful work of this project would result in an economical system for active interrogation that would help the NNSA fulfill its mission, in particular that prevention of nuclear proliferation. As far as the MTV works with us, it's been great to go to these workshops and discuss with experts the various research challenges we have, and also creates connections for internships. And of course, we look forward to collaborating in the future, especially with experts who work in active interrogation or photonuclear physics. That's maybe was not discussed heavily in this presentation, but it feeds a lot into our work. So hoping to wrap up quickly, these conclusions show from the 2D histograms that there are a lot of recoverable pulses that we could be able to recover by the use of an ANN-based PSD algorithm. And if we compare the charge integration and the ANN, of course, we show that the ANN results are promising because they show additional neutrons and it seems to show accurate pulse classification. And I'll put the caveat, the highly structured radiation environment, so for example, the highly time correlated pulses would merit additional analysis, things like time gating, or even applying different or more rigorous pulse cleaning to help us with the whole story. Next steps would include improving simulation models. Simulations have the benefit of having a perfect PSD, no dead time, so that'll certainly help us out. And then we'll do detector optimization studies, hoping to reduce photon shielding, and additional experiments, which will, especially like helium-3, which is considered a gold standard for neutron detection. I'd like to acknowledge CBT and MTV for funding, and also acknowledge the Countering Weapons of Mass Destruction Office, which has funded us for this project. And I also have references listed here. So thank you. Let me know if you have any questions.
Thank you, Chris, for your good presentation. There is one question from the audience. The question is, do you and Abbas test the ANN system with real data using either confusion matrix or the ROC curves?
So we generally train with like time of flight data, and we synthesize those pilot pulses because we have high confidence in that data. Testing wise, yes, the results that I've shown today would be the the ANN that's been trained with time of flight data, but then tested, I suppose, on the LINAC interrogations.
I guess the ROC the question on the ROC is more challenging.
Yeah. We haven't done work with ROC curves, but that's certainly something we'd like to do in the future. I know that's very relevant to, like, as we get closer to an actual deployed system, and we'd have to start considering shielding scenarios. You know, like ISO containers have specific thicknesses that we could use in our analysis. But that's something that we'd have to implement further down the line. But that's a good question.
Could you remind us what are the thresholds for the photonuclear reaction in like uranium and plutonium?
So those are generally around between 5 and 6 MeV. Thresholds for lead are about 7, and they sort of get higher for other, you know, tungsten is in that same region. So we're starting to hit all those thresholds with a 9 MeV beam.
Yeah. Good. Are there some questions from the audience? You can post your question in chat, or you can speak up on your microphone.
And feel free to email me if you don't ask during this period.
If no more questions, thank you, Chris, for your good presentation.
Thank you.